Yeah, the third project will be uploaded tonight. Okay, I'm sorry. I mean, for a little bit of delay. Okay, and obviously it's for the RNN. Okay, for the third project. Okay, so okay. So for the pre-trained model, okay, you can also, see its top K predictions. For example, okay, for the ResNet 50, okay, that we use, okay, we can, specify, okay, use a decode prediction, okay, specify, okay, it's a, Y probability with a top equal to 3. It means like we want to get a top 3 result, okay, and put it in the top K, and then, okay, we output the result. So it's going to be something like this. Okay, image 0, okay, the top 3 will be Palace, Bell Coat, Monastery, okay. The image 1 is going to be Vase, Cup, Daisy, okay, something like that, okay. So for the image 0 and the image 1, okay, the correct classes will be Monastery and the Daisy. So you can see that, okay, these two classes both appear in the top 3 of these two images. So well, that shows like the ResNet is 50 is pretty perform very well. Okay, but you can see, okay, Daisy, okay, it's only 4.87% to be Daisy. And Monastery is also the third one, only 14.56%. So, so you can see that, okay, sometimes, some classes, may look very, very similar. So it's very difficult to tell. For example, okay, I'm not sure about Daisy, but think about that. Vase and the cup. Okay, you know vase, right? 花瓶. Okay, cup, well, it's a cup of water, right? So the vase and cup from certain angle, if you do not know the scale, okay, if you don't know how large it is, they could look very similar, right? Yeah. So you can see, some of those. It's actually those classes are very difficult to tell. Okay. So, just want to give you an idea. Okay. So, so you can see it's very easy to create pretty good image classifier, okay, using a pre-trained model, okay. There are other pre-trained models available in the Keras applications, such as ResNet variants, GoogleNet variants, include like Inception v3, Inception v4, Exception, VGGNet variant, okay, and the MobileNet, and the mobile net v2. Okay, this MobileNet v2 are normally used for embedded system. Okay, because they are lightweight model. Okay, so depending on your application, okay, or whichever is good for your for you. Okay, you can actually use any of those pre-trained models. Okay, but what if you want to use an image classifier for classes of image that are not part of ImageNet? Because previously we used that for, we demo, the pre-trained model ability by using the ImageNet data set. Obviously, well, those models are pre-trained by the, if you use the ImageNet pre-trained weights, obviously, it's good for those particular data set. But if you have a data set, if you have an image data set that are different from the ImageNet, okay, so we need to use the transfer learning, right? So you guys do remember transfer learning? Okay, first we need to use like we don't use all the layers, okay, and we have our own output layers, okay, and maybe top few layers, okay, depending on how many labeled image that you have. Okay. So anyway, okay. So first, okay, assume we use a flower data set. Okay. This flower data set is also available from the TensorFlow. Okay. So we import this data set as a TFDS, and then okay, we get this TF flowers, and as supervised equal to true. This means we want the label. Okay, we don't just want the image, we want label too, and with information equal to true. Okay, so we get this, and data set size. Okay, and yeah, we have 3,670 image. I mean labeled image. Well, it's not really big one, but for transfer learning, it's probably good enough. Okay, and the class name, okay, is is also provided. I mean, so which include like you can tell there are 5 classes. Okay, which include dandelion, daisy, and so on. Okay, so basically, okay. If you have a lot of classes, 3,600 may not be enough, but with only 5 classes of flowers, I think it's probably good enough. Okay, so you can get the information about the data set by setting with information equal to true. Okay, so yeah, so unfortunately, there's only a trained data set, so you need to do like a split. Okay. So you can use like TFDS.split, okay, to divide like the data set into 10, 15, 75%, okay, and the 10% as like a test data set, 15% as a validation data set, and the rest 75% as a training data set. Okay, so you prepare them, okay, well, okay. And then, okay, you also need to, put them into batches, okay. We also need to resize them, okay. Remember, okay, because this image, their resolution may be different from the input that is required by our pre-trained model, okay. So we resize them to 224, okay. Well, based on this resolution, you can tell that, well, the model is pre-trained by the ImageNet, okay? And then, okay, so we use pre-process input to resize the image, okay, to prepare them, okay? And that's it, okay? And then we put them into batches, and we use a prefetch to prepare them, okay? Oh, we also shuffle the image in the training set to make sure, like, they are not in any particular order, okay? So pretty much we are done, okay? So we can also use data augmentation, okay, as I already told you guys about it, like earlier, okay? I believe in the last chapter, right? So you can do, for example, like the tf.image random crop, okay, to randomly crop the image, or to use tf.image that random flip left right to randomly flip the image horizontally. So there are all those different kind of like data augmentation functions you can call, okay. And if you want to take a closer look at how much support like a TensorFlow the Keras provide for the data augmentation, there's a Keras.preprocessing image data generator class. Okay, so you can load it from disk and augment them in various ways. Okay, so I will not go into the detail of this, but actually, like not only Keras provide that. I mean, if you check out the API, there are a lot of like data augmentation API available, and the different API has provide you different control. Okay, so you don't have to use Keras one. Okay, but obviously, I mean, if you want to use Keras, that's fine. Okay, but there are other API that are very conveniently available for you anyway. Okay, so if you want to know more, okay, for example, like you want to use write a pre-processing function, okay, by yourself, okay, then you can check out like chapter 19, okay, in the textbook for more detail, which will not be covered in this class, okay. So once you are done, okay, with the data set, okay, then we need to deal with the model, right? So we need to load the pre-trained model. So we will load an exception model, pre-trained on ImageNet. Okay, so here, okay, so this is okay. So we specify, okay, weight to be ImageNet, but include top to be false. So we don't want the top one. Okay, when we say we include top to be false, normally we get rid of all the layers. Okay, up to how should I say? Like normally you have like a global average pooling, which is followed by maybe some dense layers. So when you said include top to be false, the only layers you left are from the input layer all the way to the global average pooling. Okay, all the layer, beyond that will be removed. Okay, so once you have that, okay, you call that base model, and then we use the functional API. Okay, we also exclude the global average pooling. Okay, so we create our own global average pooling. Okay, and then we include a dense layer, but this dense layer, we specify n class. Remember we only have 5 classes for the flowers. Okay, and the activation to be softmax. And then, we create the model. Okay, the input is a base model input. Output is just this output. That's it. Okay. So, and we can freeze all the layers in the base model. Okay, by using like this for loop. Okay, layer trainable equal to false, and then we train the model. Okay. By several epochs, and then we need to compile the model. Okay, so because every time we freeze certain layers, we need to compile the model again. Yeah, but we didn't compile the model initially anyway. So okay, we provide like optimizers information, and then we compile the model. Okay, to provide like the loss function, what optimizer to use, and the performance metrics, and then we train the model here. We only train for 5 epoch because we use a larger learning rate, which is learning rate is said to be 0.2, so it's a large learning rate. So because this is exception model, okay, so it is quite large. Okay, the model is quite large. Okay, and even your image, like are the real image. Okay, so it's no longer just like the fashion MNIST example that you can train the model so quickly. Okay, this one will take some time, and if you have GPU, it can help you to speed up the training. Okay, if you don't have a GPU, okay, you can use GPU runtime from the Colab, okay, the Google Colab. They can let you use the free GPU. Okay, I think many of you already know that. Okay, so this is a link to tell you how to set up the Colab. Okay, if you haven't done that. Okay. So after you finish this initial training, okay, the validation accuracy should be around 75 to 80%, and that's it. Okay. Then you should unfreeze all the layers by using this command, and then set a smaller learning rate, and compile the model again, and train the model again. Okay, so it should reach around 95% accuracy. So on the test set. So this is one example to showcase you to use like the pre-trained model for the real CNN pre-trained model for transfer learning. Okay, it's no longer like the small example that we show like in the previous chapters. This is for real, but it'll take some time. Yeah, it'll take some time. Okay. So we are finally done with all this CNN stuff. But the next topic that we are going to move on is the, what should I say, the some stuff that is in addition to image classification. Okay, for example, the classification and the localization. Okay, if you want to localize the object, not just classify object, but also locate where this object is in the image. The localization of an object can be represented as a regression task. You pretty much need like 4 numbers to locate one object. Okay, so normally it's like the horizontal, vertical coordinate of the object center, as well as the height and the width. So all these 4 numbers are, can be obtained by the regression. Okay, so you need like 4 neurons. Okay, 4 output neurons. Okay, to output those numbers. Here, okay, this is one way to represent that. You can also have like maybe like the upper left corner of the object, and then the width and height, or the upper left of the bounding box, and the lower right coordinate of the lower right of the bounding box. Okay, so whichever it is. Each bounding box requires 4 parameters. Okay, so just want you to understand that. So obviously, if you want to do that, okay, so it doesn't require much change to the model. We just need to add a second dense output layer with 4 units. Okay, so which normally are on top of the global average pooling layer. So that's it. So we normally train it using MSE loss. So you can, for example, here, okay, by using the pre-trained model, okay, after you add the global edge pooling, and not only you have the class output, you also have location output, but here you specify we have 4 neurons, okay, that is on top of the average layer, okay, and then obviously because you have 2 outputs, so here, okay, you have 2 losses, and you have to specify your loss weight. Well, here is an example. So we put 0.8 for the classification task and 0.2 for the localization task. If you want to emphasize more on localization task, obviously you can change the weight here. Okay, and you have optimizer and then also the performance, the metrics. Okay, so that's it. Okay, however, okay, the flower data set doesn't have bounding boxes. Okay, so what do we do? The flower data set doesn't have bounding box. So yeah, we need to add these bounding boxes ourselves. Okay? So this is often one of the hardest and most costly part of the machine learning project, the labeling. Okay, remember I told you about that. Okay, to label a large data set sometimes it's difficult. Sometimes it even require certain expertise to do that. For example, like if the if the image is like X-ray, and you want to, tell, okay, this X-ray, I mean, maybe for the lung, okay, represents certain issue, okay. Obviously, you need like a doctor's help. We computer scientists doesn't do that, right? So, but for this localization, yeah, you do need to create a bounding box, okay, for the flower data set. But yeah, the flower data set, as I mentioned earlier, we only have like 3,700 image, okay? So it's not that bad, okay? There are, certain labeling tools available, okay? For example, like, the VGG image annotator, label IMG, open labeler, image lab, okay, all these are freely available, okay. My students have used label IMG, and it is pretty convenient, I mean, by the way, okay. And there are also like, commercial tools such as label box or supervisory, okay. These are like a commercial tool, okay. So you can also consider crowdsourcing platforms such as Amazon Mechanical Turk. But if you want to do that, you need to write a lot of documentation, because you need to tell your employee how to do the job, right? So sometimes, I mean, it is very difficult, okay? The time for you to write the documentation may not be worth it, okay? So it depends on, how large of the labeling task it is, okay? There's a paper, okay, by this guy, Adrina Kovashka, okay? They wrote an interesting practical paper about crowdsourcing in computer vision, okay? So you can have a look, okay? So basically, like, there are pros and cons of using crowdsourcing, okay? But my friend, okay, my classmate in other university, they call this like, before you have like artificial intelligence, you need to do like, well, in Chinese, it's like, 你要做人工智慧之前，你要先做工人智慧 ，okay? That's what it is, okay? The labeling, okay? So, yeah. So let's suppose you already obtain the bounding boxes for every image, okay? Obviously, I mean, it takes some efforts, but assume this is done, okay? So, okay, we assume for now we assume there's a single bounding box per image. Okay, why do we need to do that? Okay, keep in mind, we are talking about flower data set, right? So for each image, there may be a lot of flowers. When you take a photo of a flower, normally the flower comes in bunch, right? Each flower image may have many flowers, right? So yeah. Assume, I mean, each image only contains one flower, okay, and we already create a bounding box for that particular flower, okay. So obviously this may not be the case. We will talk about how to, remove that assumption later, okay. So you then need to create a data set whose item will be batch of preprocessed image along with their class labels and their bounding boxes. I mean, so the item, each item will, be something like that. The image, class labels, and the bounding boxes. Okay, for the class label, well, it's obviously, one of the 5 classes. For bounding boxes, remember, it's going to be 4 numbers. Okay, 4 numbers. Then you are ready to go. Okay, to train your model. Okay, so the bounding boxes should be normalized. Okay, so that the horizontal and the vertical coordinates, as well as the height and width, will be range from 0 to 1. Okay, this normalization is to avoid like sometimes if some, what should I say, like some features has a wider range, will have like a stronger impact to the model performance. So we normally do not want to do that. So to avoid that, so we will normalize like those 4 numbers in the bounding box label. Okay, so we also a lot of time we actually predict the square root of the height and width rather than the height and width directly. Why? This way, 10 pixel error for large bounding boxes will not be penalized as much as 10 pixel error for a small bounding box. What does that mean? Let's assume if one bounding box is like 100 pixel in width, another one is 10 pixel. Okay, so if you use the bounding box size directly for to calculate the error, then yeah, 10 pixel error, 10 pixel error will be 10 pixel error, regardless the size of the bounding boxes, right? Okay, but if you use a square root of the height and width, for example, so 100 plus 10, okay, so it's going to be 110. If you get square root, how much it will be? It's 10 point something, right? It's lower than 11, right? Because 11 squared is going to be 121, right? So it's going to be like around, so the square root of this, it's going to be 100 and something, right? Right? So this one, okay, plus 10, and the square root is going to be what? 20 square root is going to be 4 point something, right? Four point something. So originally, it's the original value is 10. So square root of 10 is 3 point something, right? So difference is about 1, right? Okay. And the original is 100. The square root of this is going to be 10, right? So difference is much smaller than this one, right? Okay, so you can see that if you use square root with the same error, the larger bounding box, okay, because this 10 point error, okay, 10 point pixel error is only 10%, right? And this 10 point pixel error for, if the bounding box is just 10 point, then it's pretty much 100%, right? So you don't want to penalize this one that much. So one way to do it is to use the square root. Okay? So this is the important stuff, okay? Just want you to be aware of that, aware of it, okay? So the MSE often works fairly well as a cost function, okay? But it's not great metrics to evaluate how well the model can predict bounding boxes, okay? Normally, when we evaluate the location of an object, okay, because it's a bounding box, we normally use what we call the IOU, okay, intersection over union, okay, IOU. This is the common metrics that we use, okay, to evaluate like how accurate our prediction for the location of the object. Okay, so what is IOU? Okay, the IOU is very simple. Okay, it's like this. For this flower, well, this is, I think it's an old chart. Okay, anyway, okay, so the green box represent the ground truth. Okay, assume your model gives you the red one. okay, then, okay, what IOU is going to be the area of the intersection, which is obviously this one, right? This one. Divided by the union, the area of the union. Okay, so you can tell that the union must be greater or equal to the intersection, right? If you have taken my discrete mathematics class, okay, I hope you still remember from your discrete mathematics. For two sets, the union must be greater or equal to the intersection. Okay? So as a result, okay, this value, the largest value this could be is 1, which happens when the union equal to the intersection. It's when your predicted result exactly match the ground truth. Okay, then your IOU will be 1. Okay, and the worst case is that your predicted value, predicted bounding box, doesn't intersect with the ground truth at all, right? Then the denominator is 0. Okay, then the result will be 0. So pretty much like this value is between 0 to 1. Okay, with 1 to be the best. Okay, so we normally use this to evaluate how accurate your localization, the object localization is. Okay, so in TF.keras, it is implemented by TF.keras.matrix.mean IOU class. So we have this already implemented for you, okay, if you want to use it, okay. So classifying and localizing a single object is nice, okay, but what if the image contains multiple objects? This is the issue that I was talking about, because, I mean, for flowers, you normally, when you take a photo, normally the photo contains many flowers, okay. And not to mention flower, a lot of times when you take a photo, the photo contains many different objects, right? So what do we do? Okay. So in case like that, okay, if your photo, if your picture, if your image contains like multiple objects, and this situation normally fall into the problem called object detection. Okay, the task of classifying, localizing multiple objects in an image. We call that object detection. Okay, so until just like a few years ago, okay, a common approach for the object detection is to take a CNN, okay, that we already trained, okay, and I mean to classify and locate a single object and slide it across the image. Okay, so for example, okay, this image is chopped into how many? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. 6 by 8, right? Grid. This image is chopped into 6 by 8 grids. Okay, and then, okay, our model each time take a 3 by 3 grids as input, and to identify if there's any object in this this particular small area, and then we slide it. Okay, we slide this 3 by 3 input, one grid to the right, and one grid to the right, blah 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 blah. And then when we're done with this, we go down by one grid, and then again do this sliding. Okay, and we keep doing that until all these grids are properly scanned. And then, okay, we may need to do 4 by 4. Again, why? Because, well, some object may be too big to fit in 3 by 3, right? And then you may need to do 5 by 5, right? So you see, just to do this object detection, a lot of work need to be done, right? So this is not a good approach, obviously. Okay, just look at how many times we need to have this, need to deal with 3 by 3. When you do this, let me see. 1, 2, 3, 4, 5, 6. And this one will be 1, 2, 3, 4. 6 by 4, 24. Okay, just to check every 3 by 3 grids, we need to do 24 CNN detection, and then not to mention 5 by 5, 4 by 4, 5 by 5. So it takes a lot of effort, right? So so detail, okay. So for example, when the CNN was looking at the top left, the image, it detects part of the leftmost rows, and then it detects the same rows again when it was first shifted 1 step to the right, and so on. Okay, so sorry, here. So it detects part of these rows. Okay, when the 3 by 3, the first 3 by 3, it detects part of these rows. And when we shift that one grid to the right, we still detect these rows, most of these rows. And then when we move 2 units to the right, these new rows come into the picture, okay, and so on. So you can see that, okay, another issue that is obvious is that, okay, the same rows will be detected multiple times, right? The same rows will be detected multiple times if you take this approach. So what do we do? Okay, to get rid of the issue that the same rows will be detected multiple times, there's a famous algorithm called non-max suppression. Non-max suppression. Okay, so to do this non-max suppression, okay, we need one more output. We need one more output. Okay, so basically, remember, how many outputs do we have? We have 5 outputs for 5 different classes, right? Remember, we have 5 different classes of flowers, right? So that requires 5 outputs, each outputting the probability of each class, right? So we need 4 outputs for the coordinates of your bounding box, right? So now we need one more output, okay? This output represents the probability that a flower is indeed present in the image, okay? So this output, okay, even though here we say it's a probability, but normally we call that output as objectness. Objectness, okay? It represents the degree that an object is indeed included in this image, and your bounding box has already, bound that object pretty well. Okay, so obviously, this the reason we use probability is because it ranges between 0 to 1 as well, with 1 representing the optimal situation where the bounding box completely bound the object. Okay, so you can imagine, okay, so when this 3 by 3 is here, okay, because most of this flower is bounded, but it's not completely bounded. So the output, I mean, this objectness may be like 0.7, something like that. Okay, and when this move like several units, for example, when the 3x3 move to here, because this flower will be identified with a bounding box, say like this. Then, okay, because this is bounded pretty well. Okay, this flower is pretty much completely in the picture. So it will be, this objectness of this flower will be very close to 1. Very close to 1. Something like that. So basically, okay, if you have that value, if you have that additional output value, so we are going to set a threshold. We're going to set a threshold. I mean, if that threshold is lower than certain value, okay, we will drop the bounding boxes, okay, because that don't actually contain that flower anyway, okay. So first we do that, okay. We drop the bounding box that with like a low objectness value, okay. That's the first step. The second step is find the bounding box with the highest objectness score and get rid of all the other bounding boxes that overlap a lot with it. Okay, so because, for example, now it's here. You know this is a bounding box that we have. Okay, and this objectness is great, it's high. But say, for example, once you move one grid to the right, here, maybe you will still be able to identify part of this flower, okay, with certain objectness, okay, say like 0.6. Okay, say that 0.6 objectness is good enough, and it didn't get deleted from the first step, okay. But because this one overlap with this one a lot, right? Obviously. So first we identify the highest objectness and then get rid of the lower objectness that has a lot of overlap with the one that with highest objectness. So here, okay, we get rid of all the other bounding boxes that overlap a lot with it, okay, with an IOU value greater than 60%. Okay, so sometimes we need to repeat step 2 several times until, okay, there are no more bounding boxes to get rid of, and then, okay, we are sure that there's like no flower will be counted multiple times if we use this CNN to sliding window approach to do that job. Okay, so this is like non-max suppression, one of the famous technique, okay, for object detection. However, okay, this concept, this idea is no longer a good idea, okay, because once this fully convolutional network comes out, like it is able to deal with like object detection much faster and much effective. We will talk about this. After the break. Okay, let's take 10 minutes break.